this somewhere so you can hear me correctly. I'm just letting the group know that we're on, and then we can go. Yeah. This is live. Okay, cool. So let's do this rather slowly and rather deliberately today. So hi everyone. My name is Zach, and I'm an open source software developer. And I usually work on embedded applications live, just to share my learning and to help me learn and to keep me accountable with learning small little things every day. And sometimes I actually get an opportunity to do something that is sort of semi-serious on the stream, where I'll be working on some actual product or some actual thing that I'm working on. One of those days is today. I'm working on a driver for this Shield SC18IS606 EVK. I'm working on a driver for the Shield EVB. EVB. Okay, cool. So this little board, I'm working on a driver for this little board, and it's just it's a I2C to SPI bridge. So you have if you have an I2C, what? No, yeah, it's a. Why is it saying UART host interface? Maybe you can use host interface, UART. But basically this enables you to have an I2C host and to enable to make it out into SPI controller, basically. And then, so usually SPI needs more pins than I2C. And so the thing this device helps us with is to basically does some sort of like pin expansion, because you get like out of two pins you end up getting something like that is 3 slave selects and miso mosi clock and miso mosi clock, and I think ground and power, something of the sort. So you get like you get a SPI bus if that is hooked up to your I2C bus that you can control via I2C. That's what this does. So over the past few weeks we've been working, well, past few months really, but over the past for the past little time we've been working on a driver. The driver for this application. So it's actually on the Zephyr repository itself. We've been working on a driver for this. Just one moment. I have to go do a call. Get my dog. Apologies, I'm back to the debug session. So, over the past few months, I've sort of worked on a driver on this on and off. It's not a really big thing. It's quite a small driver, and let's look for it. So we have a pull request that's up already. Yeah, there's this pull request that's up already. So my intention is, while the code is functionally correct in here, it's all here and it all seems to do what it's supposed to do. I'm not getting the sort of response I want from the GPIOs, present on the thing, because I wanted to go on a blink sort of trajectory. I want it to blink on and off, on and off, on and off, on and off. I like to turn it on and turn it off, turn it off and turn it on. But it's not working the way I expect. It's basically powered on all the time, as you can see here in my this pin in my logic analyzer statement. It's basically the level of VCC, and I would like to find out what it is that we're doing wrong that is making it go to the level of VCC all the time. And by doing so, just do some debugging, some normal embedded debugging. See if we can, for lack of a better time, fuck around and find out. Let's find out. So, ideally, number one, we should see when. So this is the beginning. This is the start of the thing. This is the initial barrage of messages. We are talking to I2C number 28, and I'll confirm this by going into the so we are talking to device number 28, and yes, ourselves, and we want to basically control this GPIO extension. And the way we are controlling this GPIO extension is by using the Blinky app, and we've provided an LED here that is LED GPIO port extension, that the extension port, and we want to control pin 2. So there's 3 pins on it, 0, 1, and 2 of that, and we've given it an active low. So it's basically adapted from the traditional Blinky, and just we want to see if we can get this thing to do the correct thing. So let's start. Let's begin. So we're definitely talking to the right place, and I see the initial barrage of messages. Perhaps the first thing to do is to look at all of these messages and decide what they actually do mean. You know, so there's an F0, there's a 2A, there's a F6, and then there's an F7, and then there's an F4, and then there's an F4. So there's an F4. These two look to be toggling of the actual device. So let's actually go see. The thing I'm not seeing is an F6. There is an F6 somewhere here. So let's actually see. What do these writes mean, and what we want them to mean? So communications example, functional description, I2C bus interface, that's why SPI interface. Sorry. Okay, cool. So we want to see function IDs and such. SPI interface. The F0, what does FD? Configure SPI interface, F0. So we do send an F0 here. I see an F000. What does that mean? So this means that is the mode then. We send all of this as zeros. So the order, we've sent it as 0. When logic 0, the MSB of the data word is transmitted fast. If logic 1, the LSB fast. Okay. When this is 0, 0, SPI clock is 0, and SPI clock is 0, 1. SPI clock is C pole 0, C phase 1. 1, 0 is C pole high, C phase low, and 1, 1 is 0. So we're in this mode. And then this is SPI clock rate, which is 0, 0. We are basically going at max speed, so that's fine. That is this SPI configuration. We don't really care about it right now. It works, so we leave that alone, to be honest. So, and then the next thing we do send, the next message we see on the bus is an F602. F602. What does F602 mean? So then F6. At reset, the slave select pins SS0, SS1, SS2 are configured to be used as slave select outputs. If these pins are not required for the SPI functions, they can be used as GPIO after they are enabled. Any combination of the pins may be configured to function as GPIO or slave selects. After the GPIO enabled function is set, the ports defined as GPIO will be configured as input only. After the GPIO is sent, the port will be configured as input only. Okay, so the data byte following the F6H command will determine which pins can be controlled as a GPIO. A logic 1 will enable the pin as a GPIO, and while a logic O will disable GPIO control. So what is it that we're sending here? What is it we're sending? We're sending F602. So F602 actually, well, let's use an online converter so that we can see hex to binary. Yeah, that's gonna be 00. No, I want to check 02 hex to binary. So that's gonna be 00. Yeah, so it's a I see. I see. So if we come here, that is a fast. This is a fast pin. This is pin. Look. This is 02. Yes. Yeah, 10. So which pin is this? This is the wrong pin. We are observing the wrong pin. Number one. Look. First of all, look at it. This is the second pin. Pin 2. Pin 1, pin 2, pin 3. Okay, cool. So I kind of have an idea. And of course, if it's an SS select, when it's high, okay, cool, fine. So it's not pin 0, 1, 2. It's actually pin 1, pin 2, pin 3. Because look, this sends a 2. This is a 2. I expected this to be the third pin. But clearly here, what it's doing is it's enabling the second pin. Let's look at the document we have. This might be even simpler than we thought. So this is 0, the 0th pin, the second pin, and the third pin. The 0, 1, 2 pin. So this is the pin that's being enabled right now, which is SS1. So I'm going to probe SS1 and we'll see if that actually works. And then we're going to see if that actually, that is what we want. So I'm going to probe SS1. I'm going to change the thing into SS1. That's different. And I'm going to okay, stop. So it still doesn't do the thing we want it to do. And this is all of that. This is the stuff that we started with. So F602, okay. Then there's an F7, we'll see. F710, F401, F404. Okay, cool. So there's an F7 in between there, that's okay. F602. Doesn't really change anything because this pin is still held high. This pin is still held high, which is yeah, it's a pin. So let's look at the logic, make sure it's PD3. So is this D3? Yeah, this is D3. Cool. Just making sure the correct pins are being watched here. So okay, it's still not toggling, basically. Pin D3 is still not toggling. So F602, that's actually enabling the second pin. As you see, 02 is actually enabling the second pin. And if we actually want to enable the pins correctly, so let's actually look at this. Let's actually look at the pin enable, because I want to enable them as 0, 1, 2, not as 1, 2, 3. I'd like to enable them as 0, 1, 2. Yeah. So let's Control E and then let's go to our GPIO driver and then let's look at this. The enable buff. Enable buff should be just do this 0 cross 0 0, and then let's come here and modify the enable buff before we send it. So this one does pin, we take the pin times 2 and then we yeah. enable buff is here. Pin position ×2. I think this is supposed to be +1. The configuration. This is the configuration that we'll see just now. But so if pin ×2 +1, so it's 0 × 2 +1, 2 × 2 +1, 2 × 2 is going to be 4. 2 × 2 is going to be 4, which is not exactly what we want when we're doing configuration. F7, 4. See, 4 is 2, 0, so it's supposed to be 2, 1, 0, 3, 1, 0, so it's like 1, SS2, 1, 0, SS2, 1, 0, SS2, 1, 0, SS2, 1, 0, SS2, 1, 0. So when you set it, you should send a 2 here. If you send a 2, if you send a 1 here, 1, 1 here, okay, cool. So the configuration should be read like this. You set it like this. You're not setting it that way. Okay, cool. So let's actually try and fix that fast before we go forward. I would like it to not be 2 here. I would like it to be the, I would like to use SS2 and for it to be so if it's SS0, SS1, SS2. So I would like you to choose 0, 1, or 2. If it's 0, it will be okay. If it's 1, it will be okay. If it's 2, it should also go to 2. But it's going to the wrong place. So I'm not shifting it the correct way. Should I be shifting it here? Pin conf. Should I be shifting it? Yes, 0. Yeah, let's see if we can shift it here. uint 8. So they don't like it when you do that. You want to declare everything at the top so that you can use it later. uint 8_t pin enable. So instead of just doing it like that, instead of just sending in the position, we should just shift it. So if it's 0, shift it by 0, just by a pin. So pin enable which is equals to is conf ever set. Alright, there's no actual variable. So pin enabled here. I would like to shift it to pin enable pin. It should be okay, should build all the way. So this should give us the correct ones. For 2, given our overlay, for pin, which pin are we choosing? 2, 0, 1, 2, we should get 4, 100, 100. So we should get 4. We should get 4. Okay, cool. So let me put this thing in bootloader mode. Number 1. Flash. Okay, perfect. For pin 2 now, we should get 100. It's probably not gonna work, but let's see. I have a feeling I've messed up, so I'm gonna run it and do the thing at the same time. Stop. 1, 2, 3. Stop. And okay, cool. So let's all shrink it out. I'd like to see this. Yeah, these are the ones I would like. Yeah. So first of all, F6. Is that enable? 2 is 0, 0. Okay, cool. So is that the enable one? F6 is enable. Okay, cool. F6 enabled 0, 0. That's not good. F6 data write 0, 0. That's not good. So let's actually fix that first. Even if we shifted that, so I would like to, we're probably gonna end up needing to use some sort of so it's 0 shift 1 shift pin number. I always forget. Operator. Which one is the one? I think it should be, yeah. I wanna see the left shift one. Logical. Bitwise, large. Bitwise. So it should be this, and then I would like left shift. I would like to left shift. So IJ. So left shift the operation multiple times by value of 2 to the power of j. So 1. Yeah, 1, 0. So which one's the position? That. And then so it's gonna be 0. Yeah. So let's do 0. 0 pin. If it's 0, you shift it 0 times, it's there. If it's 2 and you shift it twice, where am I doing pin conf first? Where am I setting pin conf? I'm not just getting it. Yeah, you see I have it somewhere. So I should make some value here. Let's do it the hard way first. Pin enable equals 0. I think I can do it as a default at the top. Pin enable, and then equals 1 shifted by the position of pin. And then we should go enable. We'll remove all this buff. Enable buff. We'll remove all these magic numbers just after we figure them out. Equals pin enable. pin enable. Isn't that what we just read? No. No, you see, that's not what we just read. So 1 into that. So it's 0 into that. If I shift 0 into this, it's 0, but that doesn't give me that. That's how many times it should be shifted. One. If it's 0, it's 1. If it's 2, it's 2. If it's 1, it's 2. If it's 2, it's 4. I think so. We'll use like some defined defaults for this once we know how to do. Once we know that the arithmetic is correct. So we're gonna go back and we wanna get this 1, 2, 3. No way. No way. We fixed it. It was this. Cool. Yeah, sure. So we fixed it. We actually ended up fixing it. So I'm gonna run it. Yeah. I'm gonna run it and we fixed it. So I'm gonna stop and I'm gonna go run. Yeah. There you go. That's it. That really is what we were looking for. That really is what we were looking for. That's what we want. It's actually blinking the LED as we want it to blink the LED. So it's doing the thing that it's supposed to do. What we need to make sure right now is we've chosen the right pin in the right place, and we're expecting the right pin. So I'm using SS012. I'm using SS02. Let's see on my overlay, it should be 2 as well. 2, perfect. And everything else is working fine. So the next thing we need to do is actually remove this constant. This constancy here. So we just need to remove this constant. There's a constant here, pin enable. It's like a prepared constant. I remember this from my last driver. It's one of those like things like you encounter only once in a while and then you forget completely. Here, let's look at it's like a prepared constant, SC18IS606. I'm super happy that works, because if that works, then our debugging session is done, which is 30 minutes. I'm super glad it does. There's some sort of prepared constant we can use so that we don't have magic numbers in our drivers, basically. The problem is I only encounter this every 6 months, and then it becomes like, oh crap, I forget again. I forget how to use it again. Yeah, field prep. This sort of field prep thing. So we're going to look at field prep? Yeah, let's go and look at field prep. Yeah, you see what's happening there? Field prep. Zephyr API. Docs. So, and then this is working. This is completely working. Field prep. Amazing. I cannot believe it working. So that was that. Field prep macro. Where is it? Is it field underscore prep? It is field underscore prep. It's a macro, and we can use it to prepare a field. And then once we prepare a field, it basically let's go in here, and then I'm gonna go field prep. Yeah, this macro. Use it in. I like this one. So field prep. Prepare a bit field element using value with mask, representing its field position and width. So it takes a mask and a value. Takes a mask and a value, and then let me look at it. I remember I learned how to use this, and then I've forgotten completely. So it takes a mask. What is a mask? What is going to be the mask there? Gen mask 5.5. Gen mask 1032. Let's go and look at gen mask. Gen mask. Get it, gen mask. Create a continuous bit mask starting from position L, ending at position H, 5500. Okay, cool. So this is a mask for, I guess, 3. I should be able to do it. So let's look at here, gen mask. So LSB mask, mode mask, frec mask. So what I need to go and define is a enable mask. So somewhere here I need to define an enable mask. I should define SC18IS606 GPIO enable mask. I already actually have one at the top, yeah. It's fine. Gen mask, gen mask. Isn't it like that? Gen mask. And then I think it starts at 10, so it's going to be 0, 1, 2, 2, 0. 2, 0. I think that's the one. And then do I need to do cc_tilde_h? Do I need to do cc_tilde_h? Do I need to do cc_tilde_h? So cool, I need to do cc_tilde_h. Okay, cool. So and then that's it. We do have caps lock W. So we do have a mask now. We've prepared a mask there for the fields that we want to 0. And then after we've prepared a mask, what do we want to do next? That's now we have a mask there. So we have a mask, and then where do we use this mask? How do we use this mask now? So we do a field prep and we give it a mask and we tell it how far. Now we have to go back and do a field prep. So it takes a value and then the mask. So this should ideally just plant over to the new thing. So the mask, the value, let me look at it. So what is this? Is this, how big is this? I want to look at the smallest one, the frequency mask. 1 0. That is 2 items. 3 2. 3 2 is 1. Is 3 and 2. 5 and 5. LSB mask is the smallest one. So let's look at how LSB mask is used. Config operation and config operation and transfile P, and so that's that is, I'm trying to figure it out. Because you don't want to move it. So if I have a mask, how does this change? Been enabled. I can't just give it 1. I really could. I could do it like this in here. I really could. I could just do it like that, but shift it that way. So ideally you're telling me is I can do and then I don't need this completely? No, I should be able to do, yeah, I should be able to do field prep SC18IS606 GPIO enable mask, and then there's that. I should give it a mask, and then in here I should go like that, because then this gives us the value we want. And if I go like that and then we go that way, and then this removes the thing. Ideally, let's see if this actually builds. Okay, and then we should put this up, and ideally it should just start working. West flush, yeah. Cool. And then if I go in here and I go here and I go like 1 2 3, yeah, it works. So we've removed the magic number, and this works okay, and this goes okay. So let's actually commit that. Git status, git add, git branch, add clang format that file first of all, dash I in place, drivers, GPIO SC1 IS606, git add drivers, git diff dash staged. So we made a mask, did that. Why did we do it times 2 and we just left it as that? I think I did something wrong, yeah. Because it's not times 2, because it's clearly it's 0, 1, 2. So 0 times 2 will go to 0. 1 times 2 will go to 2. It is plus 1. This has to be actually plus 1. I'm pretty positive this is plus 1. Even though it works as a broken thing, so I'm pretty positive this is plus 1. Although we're doing pin 2. So perhaps we should try pin 1 and see. Pin 0. It might be. Let's just try pin 0 and see. Okay. Before we even commit anything, Control E, there's that. Let's try pin 0. Pin 0 and see. So I'm gonna move this to pin 0. Okay. And then let's build it again. Put it in bootloader mode. I'm super chuffed because it's taken like 5 sessions for this thing to work, but it works in the end. Does anyone have any questions? I can see a few people online if anyone has any questions. Okay. 1, 2, 3. It works. So I'm gonna leave it as that. I think I'm gonna leave it as that because it works, and then we're gonna leave it as that and just good to that. Okay. Git status, git commit -- amend. Log -p. Will you add all those changes? Yeah. Okay, cute. And then so the formatting has been done. So now let's actually run compliance. Scripts CI compliance. Check compliance. Obviously we can actually be more clever and git status. Git fetch name. Okay. So this is all. Our tests are good. This is not ours. That's not ours. So I could git checkout. Git pull, just to make sure we're on the same level. Git checkout PR-sc C18 GPIO. Git rebase-i name. Git status. Git So yeah, there's that. And obviously Control R twister. We're gonna run tests and see if anything fails as well. Everything should work and we should be done. Yeah, everything works. And our PR should be up there. Our PR should be up here. First pushed. I just first pushed again. There you go. There you go. It's running tests. It's looking good. Thank you all so much. And that was it. That was us testing the GPIO driver. It turned out that we were enabling the wrong address, and that was the issue. And so it worked, and we are done, and that is cool. So there you go. Done. Done, 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 done. Done, 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 done. Okay, thank you all so much. My name is Zach, and I'm an open source software developer. If you wish to support me, check out my GitHub sponsors on GitHub. Feel free to subscribe or join our Discord channel, and we can always chat up and try and look at things and learn things together. Thank you all so much. Remember to be daring. Cheers.